I do not know you, but I do know that you spent time digging as a child. Something about digging a hole makes it one of the most satisfying and universal human experiences. Whether it was with a little plastic shovel on the beach or a stick in the dirt or your hands just down into the mud, we all knew the thrill of it as kids. And for some of us, the joy only builds as we grow up to be the scientists and engineers who dig the deepest hole in the world, or discover ancient civilizations, or figure out how to supply our communities with energy from stuff in the ground. All of that really complex stuff comes from one of the simplest joys. So roll up your sleeves, we're about to dig into the coolest stuff people have learned from digging a hole. If you grew up in the US, the goal of every beach trip was to dig all the way to China. I am sure other parts of the world have their equivalents, but nobody ever achieved them. And I know that because the deepest hole in the world didn't even come close to getting the job done. But we still learned a ton from that impressive dig. So here is Hank to tell you about Earth's deepest hole.
Deep in western Russia, the frigid desert contains the remnants of one of the most ambitious scientific experiments ever performed. It's a ruin now, a wasteland of jagged metal and crumbling concrete. If you search around long enough, you will find a rusted disc bolted to the earth, so unassuming that you might even try to pick it up. But you won't be able to. It's the welded shut cap of a borehole that plummets more than 12 kilometers into the earth, deeper than the deepest depths of the ocean. It's the deepest hole on Earth. It's called the Kola Super Deep Borehole, and its existence has nothing to do with petroleum exploration. Rather, when drilling began in 1970, Soviet scientists hoped to eventually drill down to 15,000 meters in order to gain a better understanding of the nature of the Earth's crust. Because the truth is, we know less about what's under our feet than what's on the other side of the solar system. They drilled on and off for 24 years, and though they didn't quite reach their goal when work came to a halt in 1994, the engineers had reached a record depth, 12,262 meters, a record that still stands today. 2 decades later, the Kola borehole remains a remarkable technological and scientific achievement. To drill it, engineers devised a new method by which only the drill bit at the end of the shaft was rotated. The lubricant, in this case pressurized drilling mud, was pumped down through a custom drill bit, allowing it to spin. Instruments had to be invented to take measurements at the bottom of the hole. What did we learn by drilling a third of the way through the Baltic continental crust? For one, there's water down there. At depth, scientists didn't believe water could be found. They suspect that the water formed from hydrogen and oxygen that were squeezed out of rock crystals due to crazy high levels of pressure that far down. Unlike groundwater, this water originated from the rock minerals themselves. Never before had this been observed. Also surprising? How about microscopic fossils discovered by Russians at depths of up to 6.7 kilometers? Researchers cataloged 24 species of single-cell plankton microfossils over the course of the project, and they weren't found in the kinds of deposits we're used to finding them in, like limestone and silica. These were covered by organic carbon and nitrogen compounds, preserved thanks to those high pressures and high temperatures so far below the surface. As for those temperatures, by the time the engineers broke through the 12-kilometer mark, where rock samples were dated at 2.7 billion years old, the heat became a major issue. Researchers thought the temperature of the rocks would be about 100 degrees Celsius. What they found were temperatures in excess of 180 degrees. It was this heat that caused the drilling to come to a stop. Engineers described the rocks at 12 kilometers as acting more like plastic than rock. Of course, as astonishing as this project was, the Kola Super Deep Borehole only made it through a tiny fraction of the Earth's layers. 12 kilometers is 3 times as deep as humans have ever gone, but the Earth's mantle doesn't even begin until about 35 kilometers below the surface. The mantle then continues for another 2,800 kilometers, the center of the inner core more than 6,300 kilometers below the surface. Put another way, this borehole, which took 24 years to drill, made it roughly 0.002% of the way to the middle of the Earth. It's a big planet, you guys.
The Kola Super Deep Borehole taught us about molecules, organisms, and conditions that we didn't have a clue existed down there. And ironically, it just scratched the surface. Imagine what we'd learn if we'd kept digging. Here's that thought experiment.
We filmed this episode quite a while ago, and as we were digging into the production, our fellow YouTuber Cleo Abram posted one on the same subject, which is great, and you should watch it. But it turns out her adventure to the center of the planet turned out to be quite different from our own, which I think is very interesting. So we decided to use the video we had already shot and tell our own story. As a kid, did you, like me, have that dream of just digging a hole at the beach and then making it all the way to the center of the earth? My friend Jeff dug a hole in his backyard until he hit the water table. It was a well. But as always happens, our dreams get cut short long before you reach bedrock. But over the years, people have kept at it. Scientists and engineers all over the world have tried digging as deep as possible, hoping to learn more about the inside of our planet. Despite their best efforts and decades of drilling, these projects have barely scratched the surface. Turns out, nearly 6,400 kilometers of planet might be a bit too much of a challenge for us right now. But what if we could do it? What if we had the tech, like in the terrible/brilliant 2000s film The Core, to blast all the way to the middle? What would we experience along the way? I'm gonna take you on a journey to the center of the Earth. On the way, we will discover huge fields of diamonds, solid rock flowing almost like a liquid, and a mysterious inner core that scientists are only just beginning to understand. But you might want to grab a glass of water, because it's gonna get hot. The first stage of our journey takes us through the crust. And if your objective is to get through the top layer of the planet as fast as possible, you probably should start in maybe an unexpected place: the ocean. Oceanic crust is the thinnest kind on Earth, maxing out at about 10 kilometers in depth, made pretty much entirely out of basaltic igneous rock. In the 1960s, the US chose this seemingly easy route with their Project Mohole, aiming to get samples from the oceanic crust off the coast of Guadalupe, Mexico. The problem is, before you even get to that igneous rock, you have several kilometers of ocean to deal with. Geologists have described drilling into the ocean floor through the ocean as being like drilling through the ground from a helicopter. It was difficult and expensive, and Project Mohole only managed to dig a hole about 180 meters deep before the money and everyone's patience ran out. Even with today's technology, honed by decades of deep ocean drilling, researchers have only penetrated a little more than 2 kilometers below the sea floor, less than a third of the distance needed to make it through the crust. Which leaves us with starting out our hole on dry land, on a nice, stable bit of continental crust. The kicker here is that the crust is a lot thicker than the stuff beneath the oceans, and we could be facing up to 70 kilometers of rock on our crustal journey alone. And as we delve deeper into these rocks, the conditions make our project a little tricky. Temperature is increased by 25 degrees Celsius for every kilometer we descend toward the planet's superheated interior. And thanks to the weight of the rocks above, the pressure increases by 1 atmosphere for every 3 meters down. Ultimately, this is what has stalled all of our real-world attempts to dig to the center of the Earth, like the Kola Superdeep Borehole, the USSR's answer to Project Mohole. Yes, in addition to having a space race where we went up, we had an inside race too, where we tried to go down, and the USSR beat us. And that one. We've talked about this amazing feat of engineering on SciShow before, and it still holds the record for the deepest hole on Earth at just over 12 kilometers. But despite more than 2 decades of drilling, this distance is barely a fifth of the way through the continental crust and 0.2% of the way through the Earth. The reality is, any real-world drilling effort will ultimately falter because at some point, things will get so hot that the metal in the drills will become too soft for them to work. There are some people working on giant lasers to do this, though. So that's cool. There is a reason we know more about the furthest reaches of our solar system than we do about the inside of our planet. There's basically nothing in between us and Pluto. Like, it's just vacuum the whole way. It's the opposite when you start going down. But remember, we are suspending our disbelief here and conveniently setting aside silly little things like material physics. So let's just say we could do more than what the Soviets did. The science of seismology, which uses earthquake waves as a kind of sonar for the Earth's interior, can give us a good idea about what we might encounter. At depths of more than 3.5 kilometers, we will still find animals in the form of devil worms, which are cool as cucumbers despite the heat and pressure. Those worms eat microscopic bacteria that live down there in the rocks too, and those simple life forms can withstand even more extreme conditions, surviving more than 5 kilometers deep in the crust. Of course, all life needs water to survive, and tiny cracks from the surface can allow fresh water to permeate as deep as 10 kilometers down. But there are pockets of salty water down there too, trapped by the surrounding rock. With no way to circulate, scientists scientists think it could have been sitting there for many millions of years and could contain ancient microbes dating from the geological past. And we'll also find ancient fossilized life here too. All fossils were once living organisms on the Earth's surface, or they're products of living organisms. You can have fossilized poop. But over time, geological processes and plate tectonics pushed them down deep into the crust. The Kola borehole revealed fossils of single-celled organisms 7 kilometers down, dating from 2 billion years ago. So our journey to the center of the Earth could take us on a journey back through time as well. However, the deeper we go through the continental crust, the less likely we are to find fossils. High temperatures and pressures reshape minerals to make metamorphic rocks with interlocking crystals that are some of the hardest in the world. Limestones become marble, mudstones become schists and gneisses, and in some places, the rocks themselves melt and recrystallize as huge blobs of igneous rock. And after 10 kilometers of digging, we will finally reach the mantle. The boundary between the crust and the mantle is known as the Mohorovičić discontinuity, or the MOHO for short. It's a place where seismic waves suddenly speed up as they pass into a rock of a new composition. Before we hit the MOHO, the walls of our hole would be lined with huge black crystals of gabbro, which frankly would make some absolutely delightful countertops. But the view changes once we pass into mantle rocks. Here, our drill hits peridotite, which is rich in glittery green olivine crystals with scattered red garnets like raisins in a Fruit Loaf. I bet you never read a geology textbook that told you that the mantle was green with red polka dots, but that's pretty much gonna be our view for the next 2,800 kilometers. Once we pass through the MOHO, we are officially in the mantle, but we're still slogging through the hard outer shell of the planet known as the lithosphere. The reason the crust and the topmost section of the mantle are grouped together is because they stick together. Even though the average temperatures are around 500 degrees Celsius, both crustal gabbro and mantle peridotite are still solid and rigid, so they behave as one. The lithosphere extends 150 kilometers beneath the oceans and 300 kilometers beneath the oldest continents. But our trip through the lithospheric mantle is far from dull, because here, scattered in amongst the green and red peridotite, we can expect to find bright flashes from a layer of diamonds. In fact, this is where most of the natural diamonds on Earth are born. Volcanic fluids are shifted around by plate tectonics, and those fluids can contain all kinds of elements, including carbon. When those carbon-rich liquids are shunted towards the bottom of the lithosphere, the high pressures and temperatures there are just right for building diamond crystals. Violent volcanic events have brought some of those diamonds to the surface in places like Russia, Botswana, and South Africa. But there's a far bigger reservoir of gems lurking at the bottom of the lithosphere. We can enjoy a few hundred kilometers of breathtaking crystalline scenery as we travel through the lithosphere, but when the increasing temperatures hit 1,300 degrees Celsius, everything changes as we enter the asthenosphere. At this temperature, it's hot enough for the mantle rocks to start behaving strangely. Now, you might be expecting to hit something like molten magma at this point. After all, we learned that it's convection of the mantle that powers the movement of the continental plates. And while the convection part is likely true, I'm sorry to say that hitting the mantle isn't going to be like striking oil, creating a fountain of lava. Nope, the upper mantle is a solid, but because it's so hot, it flows almost like a liquid, albeit really, really slowly. In this case, the mantle convection currents involve solid rock moving at about the same speed that your fingernails grow. So as far as we would see as we drilled down through it, the upper mantle is still that glittery green solid encrusted with garnets. Come back in 100 years though, and your hole wouldn't be where you left it. At a depth of around 410 kilometers, the behavior and composition of the mantle changes once again. Between here and a depth of 660 kilometers, we're passing through the mantle transition zone, which is marked by 2 changes in seismic wave speeds at the top and bottom. Scientists aren't exactly sure what's causing these shifts, but they think that it could be thanks to a huge reservoir of water trapped there. It's likely that there's about 3 times the amount of water down here as there is in all of the oceans. But before you get carried away imagining a sloshing shell of liquid down there, this is not like a subterranean ocean. Instead, this is water that is bound up inside crystals of a mineral called ringwoodite, which only forms at the precise temperatures and pressures found at these depths. So the next time you see somebody on Instagram saying there's a giant subterranean ocean, you can be like, no, ringwoodite, like I do, every time. The water in the ringwoodite would make these crystals bright blue. We might not be able to dip our toes in the mantle ocean, but we can enjoy 250 kilometers of beautiful blue rock as we descend nonetheless. Just don't touch it. Don't touch any of this. At the end of the mantle transition zone, ringwoodite is no longer stable, and our drill tip might begin to struggle a bit as it enters the lower mantle. Here, things are hotter still, averaging around 3,000 degrees Celsius, but the pressures of nearly 700 kilometers of overlying rock is enough to keep the mantle solid and stiff. Unlike the asthenosphere above, some geologists think that the lower mantle doesn't convect, but slowdowns in seismic waves seem to suggest that there is still some structure down there. Specifically, there are two massive blobs sitting opposite one another like earmuffs on the outer core, roughly under Africa and the North Pacific. And when I say massive, I mean it. Each one is twice the size of the moon. Scientists think that the seismic waves slow down here because the blobs are iron-rich, but there's some disagreement about where they might have come from. Some speculate that they are domes of extra hot material that's rising up from the core and interacting with the colder mantle around it. But there is another more intriguing possibility, that the blobs are the remnants of a cataclysmic event in the Earth's past, like the planetary impact that created the moon about 4.5 billion years ago. That could leave chunks of very different rock buried deep in the mantle. Now, if relics of Earth's ancient history weren't enough for you, as we continue on our journey toward the bottom of the lower mantle, we find ourselves in yet another reservoir of diamonds. They form thanks to interactions at the mantle's lower boundary, as water molecules split apart and react with iron carbide. This kicks carbon out of the core, where it's forged into diamonds under extreme pressure and temperature. Since they have more than 2,800 kilometers of rock above them, most of these core mantle diamonds will never make it to the surface. But some scientists actually believe that the famous Hope Diamond may have come from the deep mantle. After drilling down for 2,890 kilometers, we have finally made it through the mantle and into the outer core. The temperature here has risen gradually to nearly 4,000 degrees Celsius at the core mantle boundary, and for the first time, our drill tip is biting into a completely new kind of material. Instead of rock, we are now drilling through metal. Specifically, an alloy of iron and nickel with some other elements such as gold, platinum, and cobalt. Because of the high temperatures, this metal mix exists in a liquid state. Its complex motion is affected by the planet's rotation, and turbulence in the outer core is responsible for generating the Earth's magnetic field, which I am a huge fan of. It's great. However, this is not something that you could go swimming in, and not just because it would sear your skin off. It's because this liquid is thick. The high pressures at this depth mean that even at the top, the molten metal is about the same consistency as peanut butter, which I have never tried to go swimming in, but don't think I would be good at. And it gets thicker, like thicker than tar towards the bottom. So while the outer core's motion is very significant on geological timescales, we wouldn't exactly be swept away as we pass through. By the time our hole is 5,150 kilometers deep, we officially enter the inner core. Here, the temperature is around 5,500 degrees Celsius, similar to what you might find at the surface of the sun. And the pressure, which has been increasing all the way down, is now 3.6 million times that at the surface. The material we've been drilling through for the last few thousand kilometers has not changed, but despite the extra heat, the iron-nickel alloy is no longer a liquid. Instead, the intense pressure is enough to force the metal back into a solid. Curiously, the solid metal that forms under these conditions is unlike anything you would find at the surface. It exists as extremely tightly packed hexagonal iron crystals that are aligned north-south by the Earth's magnetic field. I like to imagine that it looks like a metallic version of the Giant's Causeway in Ireland, or the Devil's Tower in Wyoming. There's a little more than 1,200 kilometers of these close-packed iron crystals before we officially reach the center of the Earth. But there's one more surprise waiting for us on our way. Inside the inner core, At a depth of some 5,720 kilometers, there is an inner core, like a pit inside of a piece of fruit, which scientists have only recently discovered and still know very little about. First theorized in 2002, its existence was confirmed in 2019 thanks to seismic waves from some extremely strong earthquakes. Researchers realized that seismic waves were traveling at very different speeds depending on which direction they were going through this part of the inner core, which is thought to be thanks to another difference in crystal structure. One possibility is that the iron-nickel crystals switch to being aligned east-west instead of north-south, as if our metallic Devil's Tower had been turned on its side. What is less clear is why there's a 650-kilometer thick ball of crystals on their side in the center of our planet. It could be a fossilized record of some major event in the Earth's past, but at that depth, we may never know. So here we are. After 6,371 kilometers of drilling, we have made it to the center of the Earth. We've traveled through the solid rock of the lithosphere, the solid flowing rock of the mantle, liquid metal of our outer core, and the crystalline metal of the inner core. If we kept on digging now, we would just get to see it all again in reverse, with the added challenge of gravity working against us. It took the Soviets 24 years to drill through 12 kilometers of crust for the Kola superdeep borehole. Even if we managed to match that pace despite soaring heat and pressure at 2 years per kilometer, it would take us nearly 13,000 years to make it all the way through our planet. So, if you're on the beach and serious about making the trip, you better start digging.
I was not prepared to meet devil worms, but maybe I should have been. After all, the center of the planet is very, very hot. And somewhere along that scorching 13,000-year journey to the center of the Earth, you'd probably encounter the world's most common mineral, because it's everywhere down there. Go ahead and take a guess as to what it is before Hank tells you. I bet you'll be wrong.
What's the most common substance in the human body? Water, of course. That's every kid's go-to science fact. Well, what is the most common substance in the world? Not water, because yeah, if you look at a map, 70% of it is covered in water, but our planet is not flat. It goes down. And remarkably, the most abundant stuff in the world is a mineral that is exceptionally rare on the surface. In fact, it is so rare, scientists didn't even have a name for it until 2014. And it is part of a larger group of minerals called perovskites that have some pretty incredible properties, including possibly unlocking the next generation of green energy. If you could dig down 660 kilometers beneath the Earth's surface, you would hit a layer of hot, dense rock called the lower mantle. And this is where the most common mineral calls home. Of course, we would never succeed in drilling down to anywhere near the upper mantle, let alone the lower mantle, so we can't just grab a sample of that hot, dense rock to figure out exactly what minerals are down there. But scientists can and do conduct lab experiments where they put rocks under the extreme heat and pressure that you would find in the deep. And it's from these experiments that we've learned the most abundant mineral in the lower mantle has a structure with this chemical formula. Each crystal of this stuff is made of repeating units of 1 magnesium atom, 1 silicon atom, and 3 oxygen atoms over and over. As for what this mineral is called, well, turns out mineralogists are a bit weird when it comes to naming things. They have a rule where in order to give a mineral an official name, you must be able to study and describe a sample that comes from nature. Making it in a lab isn't good enough. And this mineral just doesn't like to exist at the temperatures and pressures that you find outside of the lower mantle. The crystal structure can break down over time, turning it into a different mineral made up of the same ingredients. So while scientists can occasionally stumble upon a mantle rock that's made it to the Earth's surface, say by coming up through a volcano or from a tectonic plate shifting around, the mineral you can hold in your hand is often not the one you're actually looking for. But after decades of searching, scientists finally struck not literal gold in 2014 when one team tried looking at rocks that came not from the Earth, but from outer space. That's right, they carefully studied the minerals in a meteorite, because when this space rock crashed into the planet's surface, it momentarily experienced around 24 gigapascals of pressure and got heated up to around 2300 Kelvin. In other words, conditions that match what you would find in the Earth's lower mantle. And upon extremely close examination, and the team found a tiny grain of the mineral they were looking for. With a naturally occurring sample in hand, the thing that makes up 38% of our planet's volume and the most common mineral in the world could finally get a name: Bridgmanite. But here's another weird naming thing mineralogists do. Sometimes they'll group a bunch of different minerals under one umbrella term, not based on the elements they're made of, but the ratio between the different elements they're made of. Since Bridgmanite crystals are made from repeating units of 1 magnesium, 1 silicon, and 3 oxygen atoms, that makes it belong to a greater group of minerals called perovskites. Not because it's made of magnesium, silicon, and oxygen, but because it fits into this generic formula, ABX3, where A and B are positively charged ions and the X's are negative. That is what all perovskites have in common. The first perovskite mineral, which you can actually just call plain old perovskite, was discovered in Russia back in 1839. To distinguish it from all the other perovskites, you would also see it called calcium titanate, because its crystal unit is 1 calcium, 1 titanium, and 3 oxygen atoms. But nearly 2 centuries later, scientists have found a ton of different element combinations that you can slot into this pattern. In fact, of all of the metallic elements on the periodic table, you can use over 90% of them in a perovskite mineral. And I do mean use. Some perovskites are found in nature, and some are made in a lab, and those lab-grown perovskites have some pretty tantalizing applications. Since 2009, scientists have been very interested in how halide metal perovskites, meaning those 3 X atoms are a halogen like fluorine or chlorine, could be used to revolutionize our solar panel technology. Today, the light-collecting cells in most solar panels are made with silicon-based crystals. They work pretty well, but they could be hard to manufacture. The silicon crystals themselves need to be practically flawless, with almost no impurities for them to do their job efficiently. So they have to be heated up to like 900 degrees Celsius to make sure there aren't too many defects. Meanwhile, perovskite crystals can perform just as well as silicon ones with many more imperfections. And to process them, you only have to heat them up to like 100 degrees, making perovskite solar panels not just cheaper to manufacture, but more environmentally friendly because you don't need as much energy. There's also the fact that you can create different perovskites, each with its own preference for the kind of light it likes to gobble up, and you can combine them to maximize how much sunlight you are converting into electricity. It's all very exciting. I spend a lot of time reading about perovskites. So, why haven't we all switched to perovskite solar panels? Well, there are a few catches. Durability is the biggest one. These synthetic perovskites have a tendency to decompose when they are exposed to moisture or oxygen or light. Those are all things that happen to solar panels. So early versions of perovskite panels lasted for mere minutes, and thanks to a decade plus of research, today's can last for months. But that's not good enough to compete with silicon, whose solar panels can last for decades. Another major issue is the fact that the best metal we've found to slot into that generic perovskite crystal structure is lead, which is rather famous for being nasty to both people and the environment if you're not very careful with it. But despite these hurdles, research into perovskite solar panels is moving very fast. In 2009, they had an efficiency of 3%, meaning they could only convert 3% of the solar energy shining down on them into usable electricity, and today it's over 25%, which rivals the best silicon solar panels. Researchers are also working to develop better seals that can keep moisture out, keep any lead in, and so forth. And in 2022, one team claimed that they had developed a perovskite solar panel that can last for 30 years. But I guess we won't know for sure for about 30 years. But one of the most promising ideas in research is to create tandem solar panels that can combine the strengths of both perovskite and silicon. In fact, this crystalline partnership seems to produce a more efficient panel than you would get from either perovskite or silicon on its own. So while one perovskite gets to stand up on a podium and hold a little trophy for being the most common substance in the world, another might hold the key to taking better care of it.
We find some amazing things if we dig deep enough, but it's not just materials for futuristic tech. We also find the past. Let's explore how digging revealed the first city in North America.
They often don't get as much attention, but North America had major cities long before European colonizers arrived. There was Tenochtitlan with the Aztec Empire and Tikal with the Maya, but there should be another name on that list too, Cahokia, built by the group known as the Middle Mississippians. Cahokia was a major city that existed near what is now St. Louis until about 1350. At its height, it was the biggest and most politically complex metropolitan area in the Americas north of Mexico, and it rivaled cities like London in size. size. It would have contained 200 earthen mounds with open plazas, thousands of houses, temples, and public buildings, all organized into districts. Things weren't always like this, though, and the path to Cahokia's rise meant a huge shift in how people had lived in the area. At least, that's what we think. The residents of Cahokia left behind no written and essentially no oral history. So to learn the story of this revolution that happened nearly 1,000 years ago, we've needed some serious archaeology. Cahokia is found in an area called American Bottom. Situated between a number of major rivers, the region was a floodplain filled with diverse habitats including open water, marshes, and forests, and dry upland areas. But before we get too far, it's worth noting that Cahokia is a name given to this city much later by European settlers. We don't know what the people living there called it, and actually, we don't know what they called themselves. Today, archaeologists just refer to them as members of the Middle Mississippian culture. But we do know that these people had been living in this area for a long time, practicing agriculture and shaping their environment even before they built Cahokia. One of the ways scientists can figure out these kinds of things is by looking at pollen assemblages. Plants produce pollen every year, and some of it can settle into the ground or water, and pollen preserves really well thanks to their tough outer shells, which protect their little packages of DNA from drying out or being destroyed. So by looking at places where pollen collected year after year, scientists can work their way backwards to guess what types of plants were around throughout history. Here, for instance, we see tree pollen disappear around 450 CE, while pollen from what were probably crop species becomes more common. Overall, that paints a picture of people clearing away the forest in the floodplains and uplands, followed by a rise in agriculture. At the time, they were probably growing species like sunflower and squash. But then, around the year 900, we see the introduction of a new important crop: corn. It was probably introduced to the area from the southwest, and there are a couple forms of evidence for its arrival. For one, scientists can just straight up find the remains of corn plants buried in the earth. They've also found starch grains that look like corn stuck to the sides of pots. But corn also left signatures in the environment. Notably, many plants use a type of photosynthesis called C3, but maize plants use C4. Exactly what's happening in each type doesn't matter all that much here, but what's important is that they make slightly different sugars. Each kind has a slightly different ratio of light to heavy carbon isotopes, or carbons with different numbers of neutrons. This all means that if you have a lot of C4 plants, they will leave a specific signature behind, and it is a signature scientists have found in lake sediments near Cahokia. Overall, it looks like corn was introduced around 900 CE, and over the next few centuries became increasingly important until it was the crop people ate. In fact, corn agriculture may have been part of what led Cahokia to becoming a booming city. Growing corn requires people to stay in an area more than the crops that had been growing previously. And as people settled down more, they could grow more corn, and villages could get larger in a kind of recursive cycle. Excavations of the nearby area suggest that's essentially what happened, maybe in just a few generations. The villages grew in size and complexity, and this trend seemed to be holding steady until around 1050, when Cahokia experienced what sometimes called its Big Bang. Here, archaeologists see a number of really rapid changes, like a sudden population boom, what seems to be a new class structure, and massive construction projects. As for why this Big Bang happened, we're not entirely sure. The increased maize production probably played a role in at least supporting what was about to happen. But the actual change may have been due to some innovation or something about labor and politics. It's not clear based on the evidence we have. But we do know that the end result was impressive, especially the construction projects, like Monk's Mound, for instance. Rising up 30 meters, or the equivalent of a roughly 7-story building, the mound covers a huge area, features distinct terraces, and was topped with a long, tall central public building. Details on how exactly Monk's Mound was built can be hard to come by, but archaeologists can use excavations as well as sediment cores. That's where you drill up columns of earth and basically make a cross-section of an area area to investigate how it changed over time. Those cores and excavations have unearthed features like vertical wooden posts and paved limestone layers. And that all suggests Monk's Mound was probably built by layers of soil and clay transported by hand in baskets. Meanwhile, the city itself also underwent a dramatic rearrangement. Scientists can see that areas that had been residential were commandeered for city or elite use. Also, houses in Cahokia shifted away from being arranged around courtyards to what appears to be a planned grid system. They've determined this partly through excavations, but also with techniques like magnetometry, which allows them to peer underground, no digging required. Magnetometry is based on the fact that different soils and materials interact with the Earth's magnetic field in subtle but detectable ways. For instance, certain objects like metal tools, fire pits, or volcanic rock interact with the Earth's magnetic field more, while building foundations or limestone interact less. So by walking over an area with the appropriate tools and then making a map of our results, we can see signatures of what may be old walls, ditches, and other construction. One of the most astounding things about Cahokia at its height, though, was just the sheer number of people living there. It looks like the population multiplied by a factor of 5 to 10 really fast over the course of about 50 years. Estimates of its maximum population range from about 10,000 to 20,000 people. And if you're thinking that doesn't sound like that many people, remember that having megacities just about everywhere is a pretty recent occurrence. Cahokia wasn't the biggest city in the world. Places like Constantinople and the Chinese city of Kaifeng had populations in the hundreds of thousands. But it still rivaled other major cities. Like London's population around the year 1100 was about 14 to 18,000, and Rome was only about 30 to 40,000. One of the ways that scientists have been able to get at these numbers without, census records is through something called fecal stanols. Fecal stanols are organic molecules from the gut that are passed out through feces. So yeah, about as lovely as you imagine. Like pollen, they can stick around for centuries in things like lake sediments, and the amount we see closely relates to population size. Amazingly, scientists can also tell that quite a lot of people who'd moved to Cahokia came from a fair ways away. Like, we know that people living here had connections with folks living as far away as the Gulf Coast and the Great Lakes. We can see evidence of this by the fact that people had exotic goods that wouldn't be easily found in the area, like shell beads. There are also a number of distinctive burial customs present around Cahokia, which implies people were bringing their cultural practices with them from afar. We can also find evidence of migration by looking at the ratio of strontium isotopes in people's bones and teeth. Strontium is an element naturally found in rocks, soil, and groundwater, and it comes in different isotopes. The exact ratio differs from place to place based on the geology of the region. When an animal ingests it, the strontium sometimes chemically acts like calcium and integrates itself into bones and teeth. Unfortunately, signatures aren't always unique to one area, so we can't use them to say for certain where people were coming from originally. But since scientists can define a strontium signature for local people, we can say at least that they weren't from here. And as many as 20 to 30% of residents had distinctive, not from Cahokia signatures. What may be most fascinating, though, is that besides the city becoming much bigger, it also appears to have become much more stratified, with evidence of work specialization and what you would call an elite class. Some of this experts can infer from other evidence. The planned nature of the buildings means we'd need logistics and a large labor force, for instance. But we also do see archaeological evidence, like how people ate, which we can tell by looking at animal remains people left behind as they prepared food. As time goes by, some groups consistently had more access to the best cuts of meat, like the hindquarters, while others ate more low-quality parts. Our most dramatic evidence, though, probably comes from what we've found of burials. Certain graves have included indications of status, such as grave goods, like thousands of shell beads or exotic artifacts. Other burials included what appears to be mass burials of people, likely enslaved people who were sacrificed and buried underneath the elite individual. Overall, this paints a picture of a society that fairly suddenly grew in size, complexity, and stratification. But Cahokia would not last. Its population peaked around the year 1200 before going into a fairly rapid decline, and by about 1350 the area appears to have been abandoned. The reasons for this are speculative. We don't know, but people have suggested a number of options. One is that flooding might have increased. Cahokia was built in a floodplain after all, and we can tell there was more flooding thanks one last time to those sediments. We can see the kinds of deposits we normally see during intense flooding show up, like clay and fine silt. Some have even suggested that this flooding was due to the deforestation we mentioned way back at the beginning of this whole saga. Without trees, erosion increased, leading to more runoff, causing larger floods. Alternatively, it might have been due to changes in the climate as a relatively dry spell ended and more rain started to fall. Other people have blamed some sort of social unrest. Scientists have unearthed what looks like defensive palisades popping up around here, which is a kind of defensive wall. In the end, it is not clear what happened, and there is still a lot to understand, including how exactly these features were built and what they were for. And that's not even including all the questions we have about the people who lived there. But through careful analysis of things like sediment cores, magnetometry, and isotopic signatures, scientists can at least piece together parts of the dramatic shift that happened here nearly 1,000 years ago.
Not to toot my own horn, but I feel like I've dug for a lot of different stuff. I've dug to find insects, I've dug for cool rocks, I've dug through a giant pile of laundry to find the other sock, but I've never dug for DNA. So kudos to the scientists who figured out that was possible.
You probably think most of what we know about ancient life comes from fossils, like bones and stuff in the ground. Well, it turns out that there are lots of other clues about the history of living things that are just waiting to be dug up. It's just that they are a lot smaller than even your tiniest fossils. Like, I definitely can't see them small. I'm talking about ancient DNA. These little bits of really old DNA are in soil, as well as other places like ice and at the bottoms of lakes or oceans, and together they are what scientists call sedimentary DNA. They are leftovers of long-departed plants and animals, sloughed off flakes of skin and pieces of hair, dropped feathers and eggshells and fallen leaves. And because of advances in our ability to purify, amplify, and analyze DNA, we can now use those remnants to recreate what Earth looked like tens or even hundreds of thousands of years ago, all without fossils like bones or teeth. Someday, sedimentary DNA may even tell us about life on worlds beyond our own. And it's kind of amazing that scientists can find this ancient genetic material at all, because DNA isn't exactly a robust molecule. Once it's exposed to the elements outside cells, DNA breaks down easily, especially in hot temperatures. So it's no surprise that some of the oldest sedimentary DNA comes from samples taken from some of the coldest places on Earth, like glaciers in Greenland or Siberian permafrost. But there are other ways DNA can stick around. DNA can bind to charged particles in the soil, specifically in clay, which protect the molecules from getting chewed up by enzymes that are released by microbes in the dirt. And sometimes those microbes can help save the DNA too. Instead of breaking it down, bacteria can actually incorporate sequences of other organisms' DNA into their own genomes for safekeeping. But to unlock the secrets that are kept in sedimentary DNA, scientists have to find it and amplify it. For this, paleobiologists use a technique called polymerase chain reaction, or PCR. They extract the DNA from a sample of mud or ice or whatever they're interested in, and then make lots of copies of certain stretches of it so they can get a closer look. To do this, they add a bunch of nucleotides, compounds that are the basic building blocks of DNA, along with an enzyme called DNA polymerase. The enzyme uses those blocks to replicate the DNA, ultimately making millions of duplicates. Armed with those copies, scientists can then sequence the DNA and find out what sorts of plants and animals once occupied that little spot of mud or ice many years ago. Unfortunately, PCR isn't perfect, and sometimes DNA polymerase amplifies the wrong thing, like DNA from the researcher and not from the soil sample. With a small cough, a tiny droplet of saliva can make it into the tube, and PCR is so good at what it does that it takes a minuscule amount of outside DNA to ruin everything. But if researchers can keep their samples and workspaces impeccably clean and keep out unwanted DNA, they can find amazing things. A lot of these things have to do with what really happened when in Earth's history, because sedimentary DNA is really helpful in giving us a sense of how old old a certain bit of genetic material might be. It's not perfect, but because scientists generally know how old the layers are that they're digging in, if they find DNA in it, it's a good guess that the genetic info is that old too. For example, in 2009, a team of researchers drilled a sample of sediment from the Yukon Flats in central Alaska, and they found sedimentary DNA in that sample that showed that woolly mammoths roamed mainland Alaska just 10,500 years ago. That means the hairy pachyderms survived at least 2,600 years longer than we originally thought. Another study found that bacteria were evolving ways to be resistant to antibiotics 30,000 years ago, well before we ever came up with the idea of modern drugs. And in 2015, researchers reported that they had found sedimentary DNA evidence of 8,000-year-old wheat in the British Isles, suggesting people were farming the land a full 2,000 years earlier than previously thought. But other scientists have since contested these results, arguing that the samples were, you guessed it, contaminated. Because we are DNA-based too, contamination is a constant concern. But some scientists think that the growing science of sedimentary DNA may help us find signs of life on other worlds, like Mars. It's super cold there after all, so if DNA is or ever was around, there's a good chance it could be preserved somewhere. We just need to find it and either then bring it back or analyze it there without contaminating it with any of Earth's very abundant genetic material. You know, easy peasy. So many secrets right under our feet.
The idea of contaminating dirt might sound a little funny, but it turns out to be a real bummer for those samples. Some digging has to be kept really clean, while other digging is done to get energy that's anything but. In fact, one of the biggest reasons that people dig today is for oil. So here's the how, why, and when of doing that.
This is a barrel of crude oil. It holds about 42 US gallons, or about 159 liters. Each day, the world consumes 88 million of them, 19 million of which are used right here in the US of A. For 150 years now, we've been living in a petroleum world. Most experts agree that over time, humans have consumed more than 1 trillion barrels of oil. How much recoverable oil is left in the ground is a subject of great debate among energy experts, but rough estimates suggest that the number is between 2 and 4 trillion barrels. But in order for those 2 to 4 trillion barrels of oil to be of any use to us, we first need to find it, and second, get it out of the ground. Neither of those things are easy, and they're getting more difficult. Fossil fuels, whether you love them or you hate them, you use them. Like a whole ton of them, in fact. You're using them right now to keep your lights on and to watch me on your computer, so you might as well understand how we find it, how we get it, and how much we have left. Before we deal with the how part of petroleum science, we should probably first ask how much, because how much oil we think or fear is left is influencing how and where we're looking for it. This brings us to a little thing called peak oil. Peak oil is the point at which we have reached the maximum rate of global oil production. This idea was first formulated in 1956 by Shell Oil employee M. King Hubbert, who correctly predicted that oil production in the US would reach its peak around 1970. He theorized that it takes about 40 years from the peak oil discovery in a given country to reach peak rate of production. In the US, discovery peaked in the early 1930s. But on a global scale, oil discovery peaked in the 1960s, which is why, since the early 2000s, people have been freaking out about the idea that humanity may never produce as much oil as it does today. Obviously, we're dealing with a finite resource here, so there will come a day when it will run out. But Hubbert's theory of peak oil has proven incorrect on a worldwide scale, mostly because he didn't foresee the enormous changes in how we discover and extract oil. Today, we're finding oil in places we never thought it existed, and in areas thought to have dried up long ago, and we're extracting it using methods and technologies that weren't around when your parents were your age. To understand the science of it, though, you gotta go back, maybe like a couple of 100 million years. Oil and natural gas are formed by the breakdown of organic materials under really high pressure and temperature in sedimentary rock. Most of the material came from the remains of zooplankton and algae that lived in the oceans between 10 and 600 million years ago. When they died, their carbon-rich bodies sank to the bottom of the ocean. As they decayed in deeper and deeper layers of oxygen-starved sedimentary rock, the heat and pressure eventually distilled the biomass into either oil or gas. And what we're really after in these substances are their key ingredients, called hydrocarbons. Like the name tells you, these compounds like methane, ethane, propane, and so on contain only hydrogen and carbon, and when they're burned in the presence of oxygen, they give off lots of heat. Over time, the liquid version of this hydrocarbon mixture, petroleum, migrates up into porous layers of rock, usually limestone or sandstone. This is where most oil and gas becomes trapped. trapped, thanks to impermeable layers of rock like granite or marble above it. When we talk about conventional methods of extracting oil, we of course mean drilling. And for a formation to be worth drilling, it needs to have at least a couple of qualities. One is enough permeability, that is, the ability for a fluid to pass through it, to allow the oil to flow easily into a well. It also has to have enough open spaces in the rock to hold fluid, which is called its porosity. Now the reality is most of the big, easy deposits with these traits that we know about, the low-hanging fruit of the petroleum world, have been discovered and exploited. Finding new ones requires better equipment and more money, and yes, more energy. One way that's improved a lot in recent years is the use of instruments called gravimeters to measure tiny changes in the Earth's gravitational field. Sedimentary rocks usually get denser and therefore have stronger gravity the farther down you go, but folds or faults in the rocks can create big pockets of lower density that could be where oil's hanging out. Gravimeters can find those pockets, which helps exploration crews narrow their searches. Geologists also often use magnetometers to detect tiny changes in the Earth's magnetic field. Because it turns out that the magnetic field too changes when oil's around. Where oil and gas are deposited, rocks are less magnetic than the surrounding rocks. So through aerial surveys, magnetometers can detect some of these weak spots to give oil prospectors some promising leads. The most common method of finding oil, however, is through seismology. By creating shock waves and measuring how fast they travel through layers of rock, geologists can gauge their density. It's like the same concept as an ultrasound scan at your doctor's office or an echo sounder used by ships. On land, seismic waves are generated using explosives or a specially designed vehicle known as a vibrosize or thumper truck. The trucks use what's called a seismic vibrator. I'm just gonna let that phrase sink in for a second. To create a shockwave on the ground, when using explosives, geologists dig boreholes up to 25 meters deep and detonate a small charge. In both cases, detectors called geophones are used to measure the shock waves. Oil hunters can use this technology underwater as well. In that case, scientists use compressed air guns on a boat instead of giant vibrators to create the sound waves. The sound waves penetrate the layers of rock below the seabed and are reflected back. Now, all of these methods are great at finding rock formations with enough permeability and porosity to hold oil, but with demand always rising and peak oil fears, we've started going hard after the unconventional stuff. Experts call them tight oil and heavy oil. Heavy oil is oil that's as dense or denser than water. Usually, oil's a lot less dense than water, which is why it floats on top of water. Tight oil, meanwhile, is found in formations where the rock's porosity and permeability are really, really low. There's oil in there, but it's not flowing like the easier places we used to drill. Here in the US, tight oil is the reason crude oil production grew by more than 1 million barrels a day in 2012, the largest increase in our country's history. The two largest tight oil formations, the Eagle Ford in South Texas and the Bakken in North Dakota and Montana, contain up to 700 billion barrels. 700 billion barrels of oil. But only about 1 to 2% of that is recoverable. The oil in these places is so tightly trapped in sandstone that conventional vertical wells proved worthless at extracting it. But in the last 10 or 15 years, engineers have figured out a few ways to get at it. One way is horizontal drilling. Instead of just dipping a well straight into a deposit like a straw, this method starts vertically and then angles to approach from the side, running the length of the reservoir in order to maximize the well's exposure to the trapped oil. Engineers have also discovered that if you create fissures in the rock by injecting a combination of water, sand, and chemicals at extremely high pressure, oil will seep through the cracks and can be extracted through the horizontal pipes. This is method number 2, and you know it is fracking. Heavy oil is an entirely different beast. The oil sands of Canada and Venezuela have dramatically altered predictions about how much usable oil we have left in the world. Alberta's oil sands may contain between 1.7 and 2.5 trillion barrels of oil, of which maybe 15% is recoverable. That still amounts to about 75% of the petroleum reserves in North America. Also called tar sands or bituminous sands, oil sands are a mixture of sand, water, clay, and bitumen, a thick mixture of hydrocarbons found in crude petroleum. Bitumen is so thick that it basically is a semi-solid with the consistency of molasses. Scientists aren't sure how these enormous deposits came to be. Some think that they're remnants of crude oil reservoirs that were destroyed microbiologically, leaving the bitumen behind. Others think that underground pressure forced it up from shale deposits where hydrocarbons soaked into the sediments and sand on the surface. Either way, since bitumen makes up between 1 and 20% of these oil sands, conventional extraction methods just don't work. It'd be like trying to drink up the world's absolutely thickest milkshake through a crazy skinny straw. So instead, Oil companies just attack it at the surface, a lot like how some minerals are mined. Some of the largest excavators and trucks you have ever seen in your life are used to scrape away topsoil and dig out the underlying tar sands. The mixture is then steamed to extract the bituminous oil and piped to refineries. But only 20% of the tar sands can be mined like this, the rest is too deep in the ground. To get at that stuff, oil companies often use a process called steam-assisted gravity drainage. It involves drilling 2 horizontal wells, one near the bottom of the reservoir and the other a few meters above it. Steam is injected into the upper well to loosen up the bitumen, which then flows into the second well where it can be drawn up. Now, you probably noticed that whether we're talking about conventional or unconventional oil, finding it is usually pretty freaking complicated. And the harder it gets for us to find the oil, the more we're pushing the limits of what machines can do and what engineers can dream up. So it's worth noting the extra effort and energy that's now required to extract the black gold from the ground. At some point, probably in your lifetime, the cost of extracting oil will get so high that it'll no longer be economically viable for either the producer or the consumer to use it, at least in the ways that we currently use it, which is pretty wasteful. And so everyone knows that it's time to start exploring alternative energy sources that don't require squeezing oil out of sand.
The simple act of digging gets pretty complicated when we're doing it to power everything around us. And even in a future where we stop digging for oil, we might still return to those holes for other reasons. At least, that's what happened after we finished extracting something else from the ground. For the last video in our compilation, here's Stefan to explain why miners are flocking back to an abandoned silver mine. I hope you dig it.
There's a ghost town in northern Mexico filled with ruined stone buildings and long abandoned silver mines that hint at the town's lucrative past. The only functional structure left is a huge suspension bridge called the Puente de Ojuela, which spans a deep valley to the south of the town. The 300-meter-long bridge was built by the same people that built the Brooklyn Bridge, and when it went up, the Puente de Ojuela was the 3rd longest suspension bridge in the world. Now, though, the area is experiencing something of a renaissance. Thanks to a quirk of geology and a little bit of luck, there's something pretty and valuable in those mines once again. Today, Ojuela, in the rural state of Durango in northern Mexico, is a ghost town populated only by occasional tourists. Like many of the ghost towns that dot the US and Mexico, its success relied on the extraction of precious metals beneath the surface. Spanish prospectors discovered silver and gold here way back in 1598, and Ojuela thrived mostly on the profits from the silver mines for around 350 years. The town became an important point on the UNESCO-recognized El Camino Real de Tierra Adentro, otherwise known as the Silver Route. That route was used for transporting and trading silver through Mexico and the United States. And this old trade route was only made possible by even older geological events. The gold and silver bearing rocks here formed when hot hydrothermal fluids from underlying magma pushed up through the Cretaceous age limestone that makes up Ojuela's hillsides. These fluids carry all kinds of rare elements within them, which are deposited when the liquid cools and crystallizes. The result is what's known as a polymetallic hydrothermal ore deposit, where the good stuff is concentrated in veins that crisscross through the main rock body. And Ojuela's metal deposits were huge. Over the years, the mines have yielded about 2.5 million kilograms of silver, 17,000 kilos of gold, and 816,466 metric tons of lead. Eventually, though, all of the shiny stuff was mined out, leaving nothing to support the historic mining town. Without its subterranean source of wealth, Ojuela was abandoned and left to fall into ruin. But this was far from the end of Ojuela's story, because these mines were also hiding a secret stash of other, much more unexpected minerals. Most of the minerals we encounter in the world of geology formed in one of two ways. Some crystallize out from a primary liquid. For instance, the olivine and feldspar that make up igneous rocks forms when hot magma or lava cooled, and the calcite that glues together sedimentary rock crystallized out of supersaturated water. Others are forged under high temperatures and pressures without melting. That's how some metamorphic minerals like kyanite and garnet form. But there's a whole other class of so-called secondary minerals that are only made when pre-existing rocks are altered at the Earth's surface. Essentially, what's going on here is weathering, a process we more often associate with breaking things down than making anything anything new. But weathering exposes rocks to water and oxygen, which they likely won't have seen while they were forming inside the crust. The minerals in these rocks are what's known as metastable, meaning that they're fine to hang out in the high pressure conditions underground, but aren't built to withstand the environment up on the surface. It doesn't take a lot of heat or pressure to alter them either. Just a subtle shift is enough to get the change going. Sometimes the secondary minerals form because elements in that primary material dissolve away, while the insoluble ones stick around. Water, oxygen, and other compounds combine with what's left behind to create a new mineral with a brand new chemical formula. All of this takes place gradually and at temperatures well below the mineral's melting point. And some of these secondary minerals have come to be incredibly useful to us over the years. For instance, weathering of feldspar can produce kaolinite, which is a type of clay used in pretty much all pottery and ceramics. Feldspars can also weather into something called gibbsite, which is one of the main sources we use to extract aluminum. Sometimes though, chance chemical alteration can conspire to create minerals that aren't necessarily useful, but they are beautiful. And at the Ohuela mine, gem collectors stumbled across some of these secondary riches in 1946, when they dug into a grotto filled with lime green bubble-shaped crystals of adamite. Remember that the town's gold and silver were originally part of a polymetallic ore deposit, meaning that there were several different kinds of metal in the hydrothermal veins. Previously, only the shiny precious metals had been considered valuable enough to be worth mining, but years of weathering made a less valuable metal into jaw-dropping crystals, zinc. Zinc and arsenic happen to be big components of this particular hydrothermal system, and so the rocks altered to make a unique collection of zinc and arsenic-rich minerals, including this adamite. Adamite is a zinc arsenate hydroxide, and the crystals can be a range of colors depending on the other elements that find their way into the mineral structure. They'll be clear or white if they're very pure, yellow if they have iron, lime green with copper, and occasionally pink with cobalt or purple with manganese. Some crystals even glow yellow or green under UV light thanks to a small amount of uranium-bearing ions within them. Naturally, the crystals grow in an elongated shape, but because their growth depends on the space they have available and the flow of water around them, they can create some interesting formations and complex clusters called druses. They can even grow on other secondary minerals like limonite, like these ones did. After the 1946 discovery of adamite in Ohuela's mines, gem collectors realized what a treasure trove this secondary ore deposit was. Exploration over the following decades revealed more than 100 other brightly colored secondary minerals scattered throughout the veins. In the mid-20th century, miners realized they could earn more from these colorful gems than they could from the gold and silver left in the mines. So Ohuela is experiencing a second life thanks to its secondary minerals. It might not be enough to rebuild a whole town, but it's enough to keep Ohuela on the map.